All right, so we're going to continue talking about Riemann sums, but we're going to add some things to it. So this lesson is on summation notation and Riemann sums. Now, summation notation is something you should have talked about in Algebra 2, but I'll review it like maybe you forgot about it. All right, so I'm just going to draw a little function. All right, and we are going to represent the area from A to B using a right Riemann sum. Okay, so in this one, the right corner of the box is what's touching the function. I'm trying to make them equal width. Okay. And you'd keep on going all the way to B. All right, so our Riemann sum that we would do is going to be the summation, which is this Greek letter sigma. Right, we're going to use k in here, and we'll talk more about it in a second, but it's from where k equals 1 to n. And that is the number, 1 to n is going to be the number of boxes. N is the number of rectangles that you find. Right, so it's going to be equal to f of x sub k times delta x, right? And so this f of x sub k is going to be the height of the rectangle. Let me spell that right. And then this delta x is going to be the width of each rectangle. All right, so the width, we'll put it like this is a delta x, this is a delta x, this is a delta x. So now the height right? So we have A. The height is actually going to be the value of our first rectangle is going to be the value of the function right there. And so that is not f of A. That is f of A plus delta x. All right. And so just a note that the first rectangle, k is 1. All right. Then if we want to find the height of the next rectangle, it's going to be the value of the function right here at this green dot. So that's going to be f of A plus 2 delta x's. So our second rectangle, k is 2. All right, and then the third rectangle, this would be f of A plus 3 delta x's. All right, so k is, k is 3 on the third rectangle. So k represents which rectangle we're talking about. All right, so if I want to do a summation for a right Riemann sum, it's going to be the summation from k equals 1 to n, so however many rectangles is n. All right, so our height, if you're looking at it, so k is 1, this is 1 x, delta x. K is 2, this is 2 delta x. K is 3, this is 3 delta x. So it's going to be f of A plus delta x times k. And then the width is delta x. So all I did for the height is I used what I just figured out using my diagram, and I just filled in this for the height. So that's a right Riemann sum, and honestly, that's the one we'll see a little bit more often, but they do like to occasionally throw in a left Riemann sum on these, and it kind of, sometimes it will throw you for a loop, but we'll try to review it plenty. Okay, so I'm going to try to draw that same function. All right, we're going to go from A to B again. It might not look exactly the same, but that's okay. All right, this time we're going to draw left Riemann sum. So this time, the left corner of the box is going to sit on the function. All right, and we would continue that all the way to B. So again, the width of each rectangle is delta x. They're supposed to be equally width. Mine isn't exactly. Okay, so now let's look at these heights again. All right, so this first rectangle, the height of it is going to be that value where that purple dot is, which is going to be just f of a. And that, again, is when k is 1. All right, the next one would be this point right here, which should be f of a plus delta x. That's when k is 2. All right, and then the third, when k is 3, is f of a plus 2 delta x. Okay, so look at the relationship of those with the k's. And then let's see if we can write a summation for a left Riemann sum. Okay, so we need to use k. We have to use k. We have to use it in a way that when we maybe multiply it by delta x, we get no delta x, then we get 1 delta x, and then we get 2 delta x. And that's when we're putting in 1, 2, and 3. So that's going to need to be a plus delta x times k minus 1 for our height. And then our width is still delta x. So when I put in 1, I get 0 delta x. When I put in 2, I get 1 delta x. When I put in 3, I get 2 delta x. That's what we need. Okay, and then the delta x is found the exact same way that we've done it in the past. So that's the width of each rectangle. So that's going to be equal to b minus a over n. So the larger value in the interval, or the upper limit minus the lower limit, divided by how many rectangles we want to have. All right, so on example 1, we're going to write a Riemann sum to approximate the integral from 1 to 5 of 2x minus 3 dx within subintervals of equal length and summation notation. All right, so what I would do over to the side is just write down what everything is. So a is going to be this value down there, the lower limit. Whoops. So a is 1. B is going to be this value here. So b is 5. So we can use this and go ahead and find delta x. So that's equal to 5 minus 1 over n, or 4 over n. Okay, if we're doing a right Riemann sum, this is the formula we're going to use. So we're going to do the summation from k equals 1 to n of f of, right, and then it's going to be a plus delta x k. So a, we just said, is 1. Delta x, we just said, is 4 over n. And then we're going to multiply that by k. Right, and then don't forget this last part. A lot of people forget it. And then we multiply that by the width, which is delta x, or 4 over n. Now, most of the time you see that this part right here written as 4k over n, which is what I'm going to do in just a second. Right, and then sometimes on the tests, they'll have you stop right there. But I'm going to take it a bit further and actually use, I got lost different here, and actually use the function we're given, 2x squared minus 3. So I'm going to do the summation from k equals 1 to n, and I'm going to find f of 1 plus 4k over n by taking 4k over n and plugging it in for x. So I'm going to multiply it by 2. I'm going to square it, and then I'm going to subtract 3 from it. All right, so all of that is this f of that. And then I'm going to multiply that by my width, or 4 over n. Right, and I know that's a lot right now, but this whole packet is talking about this plus a little bit more. All right, so let's look at number 2. So we're going to write a left Riemann sum approximation of the integral from 2 to 8 of 3 natural log of x plus 5 dx with n subintervals of equal length, and using summation notation. So you guys go ahead and write down what a, b, and delta x are, please. All right, then we're going to do the summation from k equals 1 to n of f of. All right, now this is a left Riemann sum. It's the one that's a little more difficult to remember. So n for a, I'm going to go ahead and put my 2. And for delta x, I'm going to put my 6 over n. Sorry. And let me fix that. I am going to multiply that by k minus 1. So we do delta x times k minus 1, and then we multiply again by delta x. So the left Riemann sum, you have to remember that k minus 1. Okay, then I'm going to apply the function to this. So the function is 3 times all of this plus 5. And then that multiplied by 6 over n. Now that's still approximations. So if we're looking for approximations, then that's all we do is the summation. This next one, we are finding the definite integral as a limit of Riemann sum. So this isn't going to be an approximation. This is going to be the exact value. All right, so if we want to find the exact value of the integral from a to b of f of x dx, we are going to have to use a limit. So we're going to do the limit as n approaches infinity of the summation from k equals 1 to n of f of x of k, which is the height, times the width, delta x. All right, so when we add this limit, this part right here, remember n is the number of rectangles. So if n is infinity, that means an infinite number of rectangles. And an infinite number of rectangles means the exact area. Okay. Great, and then I'll just go ahead and write this using the right Riemann sum. So it could be the limit as n approaches infinity of the summation from k equals 1 to n of f of a plus delta x times k times delta x. Now, again, it's possible that you would use the left Riemann sum too, the k minus 1. They're both perfectly fine. Like I said, this one, the right one, we use a little bit more often, but they both work. Okay, so on example 3, we're going to write the definite integral as the limit of Riemann sums. And I'm still going to start off like what we've been doing, where we write what a is, we write what b is, we write what delta x is. All right, and then I'm ready. So if we're not approximating, we are representing the definite integral. We do the limit as n approaches infinity of the summation from k equals 1 to n. So that means infinite number. We're going to add up an infinite number of rectangles. So it's going to be f of a plus delta xk times delta x. All right, then I'm going to take that, I'm going to apply the function, which is the square root of x to it. A lot of notation to write. So in the place of f of 2 plus 3k over n, I'm going to apply f, and it's going to be the square root of 2 plus 3k over n. And I'm going to multiply that by my delta x. Okay. We'll do the same thing on b. So we're going to add up an infinite number of rectangles. So to do that, we have to do the limit as it approaches infinity. And then it's going to be f of a plus delta x times k times delta x. All right. And then we'll apply the function. And our function is 4 times x squared. So 4 times what we have here in the parentheses squared. All right. So now we're going to look at some mistakes that people have made. So these, a lot of these, you're just going to like match, or you're going to find the mistake, or you're just going to fill in the box, and then at the end you're going to do some of these on your own. So a common mistake when matching definite integrals and Riemann sums is to forget or ignore the delta or the dx in the integral, which corresponds to delta x term in the Riemann sum. A common mistake looks like this. So we have the integral from a to b of f of x dx, and then someone says it corresponds to the limit as n approaches infinity from k equals 1 to n of f of x sub k. So that's just multiplying by the height and not multiplying by the width. So what is missing is the delta x term. The correct Riemann sum would be the next one, where you multiply by the delta x, b minus a over n. We're going to try the following exercise. Each of the below definite integrals is incorrectly written as a Riemann sum. The delta x portion is missing. Write in the correct delta x to make the statement correct. All right, and so we're looking at this one. Delta x is going to be 3 minus 0 over n, or just 3 over n. And so we would just need to multiply that by 3 over n. All right. Now, finishing 2 and 3 is going to be part of your assignment. Let's go on to the next additional learning resources. One of the key relationships between a Riemann sum and a definite integral is the delta x term in the Riemann sum. For the definite integral from a to b of f of x dx with the Riemann sum, the limit as n approaches infinity from k equals 1 to n of f sub k times delta x are partitions of equal length. We calculate delta x as b minus a over n, where a and b come from the definite integral and n is the number of partitions. Note that if the partitions are of equal length, then we can write that limit notation where we can move the delta x in front of the sigma. So that's possible. Thus, if we wanted to write the integral from 0 to 2 of e to the x dx, our Riemann sum would look something like that. We would have the limit as n approaches infinity of a summation from k equals 1 to n of e, and that is being raised to the a plus delta x times k. A, in this case, is 0, so you don't see it. All right, and then we're multiplying it by delta x. While the integral from 2 to 7 of e to x dx would look something like that. The difference is the delta x is different. It's 5 over n because it's 7 minus 2. And then we do have an a value of 2 that you actually see. We don't see the one that's 0. Right, in the first integral, 5 minus a over n is 2 minus 0 over n, or 2 over n. While the second integral, we just talked about that, is 5 over n. You can see that things are going on inside the Riemann sum, but identifying delta x is one important part of the process. Note that you can also write the limit as, you can write this limit, you can take the delta x and just move it in front of the whole limit. So that's possible also. Okay, so I'm going to do one of these with you, and then I'll let you all finish it. So we're going to, for the following exercise, use what you know about delta x to match the definite integral in the left column with the corresponding Riemann sum in the right column. All right, so we're going to do D. So A is -1, B is 1, delta x is 1 minus negative 1 over n, or 2 over n. So if we're looking for that, just using that to match, we're looking for the one that has that as a delta x in spine. It's in front of the sigma. It could be at the front of the sigma, or it could be in front of the limit, or it could be at the very end. So that's definitely D. Okay. So we're going to recall that the Riemann sum for definite integrals is that same formula we've talked about. The f of x sub k piece is sometimes written as f of a plus k times delta x. We know that delta x is b minus a over n, and k is the letter we're using in the Riemann sum for the partitions. On the bottom and top of the sigma, you can see that k starts with 1 and iterates all the way to n. The a is where the integral starts, or the lower limit of integration. So imagine that we want to write the integral from 1 to 3 f of x as the limit of a Riemann sum. We have the model of the limit as n approaches infinity from k equals 1 to n of, and you guys can see that. We know that a is 1. We can calculate delta x is 2 over n. So our expression will be that limit, where we'll put in 1 for a, we put in delta x for delta x, 2 over n, and then we can simplify it a little bit more like we did before. Now imagine that we want to write the integral from 1 to 3 of f of x dx as a limit of Riemann sum. And we know that f of x is x cubed. We're going to do the exact same thing. And we put in our a and our delta x, and then we put it into the function, which means we're going to cube it. All right, so I'm going to do number 1 with you. So we're going to try the following exercises. For the given definite integral, write the appropriate limit of a Riemann sum by filling in the correct information in the box. All right, so again, we're to where we need to write down what a is, what b is, and what delta x is. All right, and then inside that box, we're gonna do f of, we're gonna do a plus delta x times k. I'm just gonna go ahead and rewrite it. Okay, so a in this case is 0, and then delta x times k is 4k over n, and we're going to multiply that by 4 over n. Now, it is unlikely that you would see that 0 written. So it would just be f of 4k over n times 4 over n. Okay. And you guys are going to finish those on your own. Okay, this one is going to take it a little bit further. We're going to actually apply it to the function. And just a second. These 3 match the previous 3. So for 4, we had already written, this. So what we need to do is apply f of 4k over n. So f of x is going to be x to the 4th. So we would do the limit as n approaches infinity of the summation, that was a bad summation, from k equals 1 to n of what we had written before, which is 4k over n raised to the 4th, and then times 4 over n. Right, and let me just double check. So I'm pretty sure negative, yeah. So 5 would correspond with 2, and 6 will correspond with 3, so you don't have to start over from the beginning. All right, and then these last ones, you're doing everything. You're putting it all together. So we're going to write the definite integral as a limit of Riemann sums. So A is -1, B is 4, delta x is 5 over n. So we're going to have the limit as n approaches infinity of the summation from k equals 1 to n of f of a plus delta x times k times delta x. All right, then I'm going to apply that to the actual function, which is x squared. Okay, so f of -1 plus 5k over n applied to f of x squared means we're just going to take what's inside those parentheses and we're going to square it. Okay, so your assignment is to go back and finish anything in this packet that we didn't do together.